Okay, guys, so here we go. This is areas of plane regions, and this will correspond to assignment number 28. And again, if you would familiarize yourself with the notes and the examples before you watch the video, I think that would help a great deal. So, we want to find the area of the region bounded by these two functions here. And again, this will be assignment 28. We'll call this example number 1A. All right, so we have these two functions, y equals. They're both parabolas, by the way. Knowing that helps, but it's not imperative. But anyway, in general, I'm a visual person. I think most people are when it comes to things like this. So I would highly advocate that we sketch a rough graph of the region. Very rough, all right? Doesn't have to be perfect, so we'll sketch a graph of this. Now, when it says region bounded by two functions, we need to establish basically where these two functions cross each other, if indeed they do at all. All right? And so the way we do that, this is just algebra, would be to set these equal to each other and solve. So the idea here would be that if y equals this and y equals this, then we'll set the x squared over here equal to the 12 minus 2x squared over here and solve it for x. And here we go. Ready? 1, 2, 3. That's just algebra. All right, so we solve that for x, which we'll buzz through. I would suggest combining this 2x squared over to the other side. Combine like terms. This is all just algebra. So 3x squared equals 12. Divide by 3. X squared equals 4. This is just algebra. Square root, and it looks like these two graphs will cross each other on the x-axis at plus and minus 2. All right, so that's where the meat of the discussion is going to be. And again, I'm not going to spend a whole ton of time worrying about getting the scale perfect here. So I'm just going to put -2 here, and +2 here, and these are where we hope the two graphs would cross each other. Now, I'm also big into confirming things. So what I do, hit pause if you need to, if I start erasing too quickly. But I like to do this. Underneath this equation, I'm going to put -2 in there for x and see what ordered pair it would create. And of course, -2 squared is 4. All right? And then I'll put -2 into this one and put -2 in there. -2 squared is 4. 4 times 2 is 8. 12 minus 8, that would also be 4. That confirms that at -2 on the x-axis, these two graphs would cross at 4 on the y-axis. -2, 4. That's a point the two graphs have in common. It's a point of intersection. All right? The other thing I like to do is check the upper number, 2. All right? So 2. And by the way, notice I'm putting a gap here. We're going to talk about the fact that we're going to check a point in between here. All right, so let's leave a gap there. If you put 2 in there, 2 squared is 4. It's coincidence here. They don't have to be the same every time. And over here, when you put 2 in for x, 2 squared is 4. 4 times 2 is 8. 12 minus 8, that's also 4. So you notice that they also cross at +2, 4. It wouldn't have to be the same number as the one before. We'll see that. That'll change on different examples later on. But that's the behavior here. All right. Now, we talked before about how we find areas by integrating things. And so these are going to ultimately be our limits of integration. We're going to be integrating between -2 and 2 here on the x-axis. So pack that away for a moment. All right. But here's the next thing I think we should look for. What happens between -2 and 2? What happens between there as far as these two graphs? So we're beginning to talk about finding what I like to call the upper and lower functions. All right. And just for clarity, I'm going to make the upper one green and the lower one red to make them stand out. And it seems to me the best way to do that would be to say, well, between -2 and 2, because this is the region where they're bounded, what happens as far as which graph is above the other? That's what's above, upper. Okay, so pick a number in between there. I would recommend 0. Isn't 0 between -2 and 2? And I would put 0 into both of these. I didn't do a very good job of leaving room here, but if you put 0 in for x, this graph produces the number 0, 0 squared, right? And if we put 0 in for x in this one, and do the arithmetic, this is 12. And again, upper is going to be green and lower is going to be red, and you look at those two and you compare the two y values and you say 12 is a bigger number than 0, so that establishes that in this interval from -2 to 2, you pick a number in the interval and test it, such as 0, right? That's what we just did. Test the number, make sure it's in your interval, make sure it's between the -2 and 2. And in my mind, I'd go, okay, so 12 is a bigger number than 0, so you're the upper and you're the lower in that interval, okay? And so I underline that one in green, if you can tell, and that one in red, because 12 is a bigger number than 0. Now, it really doesn't matter what happens in between here. These could squiggle, wiggle all over the place. They do indeed happen to be parabolas. But again, just in general, your upper curve could do all kinds of crazy things, and your lower curve could do all kinds of crazy things. Doesn't matter. They're parabolas, but look, all we need to know is where do they cross, and then over that interval, what happens as far as upper, lower, okay? That's all we need to know at that point. So, if we want to know the area between these two curves, we're going to integrate this thing, because integration, again, finds areas. And if you think about it, wouldn't the area between here, between the two curves, be the area under the upper curve minus the area under the lower curve? So as the notes have outlined for you, wouldn't it make sense that we will integrate from -2 to 2, and we will take that function and subtract from it that one. We'll take the area under the green one and subtract the area under the red one. We'll take the area of the upper curve and subtract the area of the lower curve. And by the way, to relabel these, the calculus nerds of the world have determined that we should label the upper function f of x and the lower one g of x. All right? So, in general, wouldn't it make sense that the area would be the integral of the upper minus the lower, which in general terms would be f of x minus g of x. And again, the a and b would be these points of intersection. So we're going to integrate from -2 to 2, and in this case, we'll take the upper function, 12 minus 2x squared, upper f of x in general, and subtract from it the lower one, g of x. And again, it's with respect to x. Make sure to put that dx on there. And there's your setup. So in my opinion, once the thing is set up, the rest of it is very mechanical, whereby now we go back and we integrate and evaluate and all that, because we're going to get a number here when we have a definite integral. So the point would be, this should be a flashback now to previously discussed material. Find your antiderivative, do your evaluation. I would recommend, before we do that we simplify this if we're able to, and I would throw out there that the -2x squared and the -x squared would be like terms. So how about 12 minus 3x squared? Simplify it. Find your antiderivative. I'll go one more step with you. So wouldn't this term have an integral, an antiderivative with respect to x of 12x? And this one would be 3x cubed over 3. 3x cubed over 3. Notice the 3's cancel. That's just x cubed. And that needs to be evaluated from -2 to 2. All right? Let's check this. The derivative of that is 12. The derivative of that is 3x squared. Remember, you can always work it backwards to check. And then evaluate. Stick the numbers in. Stick the 2 in there for x. Crunch, crunch, crunch. All right? And then stick the -2 in there. And crunch, crunch, crunch. And like I've been doing, and I've been doing it this way for a long time. A lot of people have told me, once you show me the setup, all right, Mr. Strawberry Shortcake, I'm good from there. Once you can get me to that integral, in theory, you should know what to do from what we've talked about in the past. So once you go ahead and stick those numbers in and evaluate it and everything, I did the work ahead of time, you should be getting the number 32. And there would be 32 square units. It's an area. I don't know what the units are, square feet, square inches, whatever the question might be, we'll just put 32, and that's the area between. So again, as we've talked before, we integrate this thing, we evaluate it by sticking those numbers in. I'd love to show you every step, but I don't think I should have to do that. And then of course we all know that you celebrate. And then we talked before about once we do that, then someday we're going to graduate, aren't we? Okay? So after we integrate and evaluate, celebrate our success, then we're going to graduate, right? And then, of course, the biggest step there at all would be to compensate, right? Whereby you come back to the people who helped you through this, right? And you would compensate them because you're now a world famous engineer from all the calculus you learned, and you come back and you go, hey, I really want to show my appreciation to you for helping me graduate and become a world famous engineer. And that's where you come back, and that's the really most important step, right? So, come on, man, show me the Benjamins. Make it rain.